Hello everyone, my name is Fernandes and I am a graduate of the Federal University of Itajubá. Today I will be presenting our research titled G-BPMT, an interactive tool for guided modeling of business processes in BPMN notation. The presentation is organized as follows: Introduction, background, methodology, results, and conclusions. First of all, the business process management is a cycle used as a means to convert a traditional process in an organization into a digital one. However, the process discovery phase of this cycle is highly time-consuming for process modelers. I want to highlight three specific points for that. Firstly, the lack of BPMN proficiency means domain experts may not even know where a process begins and ends, much less describe it in a way that a modeler can easily model it. For example, they might omit crucial information about process divergences. This example aligns with my second point, fragmented data. A domain expert may lack the granular details of a specific task or the tasks of a specific participant, which can introduce inconsistencies into the model. Finally, alternative elicitation methods still rely heavily on well-structured textual descriptions, assuming the various skills these experts lack. The problem addressed in this research is that the interval-based approach to process discovery relies heavily on manual mediation to translate business vocabulary into formal notation, making the initial elicitation slow and inefficient. The motivations are to bridge the knowledge and reduce the cognitive friction for non-technical users, decrease the time and effort to elucidate the process in the discovery phase, and finally, to support the teachings of BPMN in academic and professional environments. The hypothesis we aim to prove is that if a domain expert uses a guided interface to generate a baseline model, the subsequent interviews of the discovery will be significantly more productive and require less manual rework. The specific objectives are to collect process information in an orderly manner and convert it to a commercially compatible BPMN diagram, in other words, a .bpmn file. Validate the consistency and completeness of the model, granting that the generated model are in fact useful, and finally evaluate the perceived usability of the tool as a means to guarantee that it will be easy to use for the domain experts as listed on the first motivation.
In related works, some alternatives face clear limitations. Frederick extracts BPMN structures from text, but rely on semantically rich data that contradicts the situation with real intervals. Ivanchevik converts linear descriptions into diagrams, but replaces the BPMN barrier with their own grammar syntax. Lastly, Declasse and Castro mapped approaches like simplified languages or digital games, but they still demand specialized techniques or highly controlled environments. The design science research methodology, DSRM, was utilized to guide this applied exploratory research using a qualitative quantitative approach. Guided by the 6 steps of the DSRM framework and a problem-centered entry point, this study progresses from problem identification and objective definition to architectural execution. Having already established the initial phases, I will now detail our design and development choices. The demonstration and evaluation stages are presented within the upcoming results, fulfilling the final communication phase through my thesis defense and this presentation. The artifact was designed around a standard process discovery interval mapped out by an expert modeler. It replicates the logical sequence, guiding the participant from the initial process definitions, the part highlighted in blue, into an incremental loop for the other parts of the process, the part in green. Within this loop, the process diagram dynamically grows, diverges, or converts, depending on how the user responds to the guided questions. This table outlines the functional and non-functional requirements alongside the evaluation criteria. Together, the functional requirement number 1, non-functional requirement number 1, and both evaluation criteria number 4 and 5 were established to guide the core development goal. By optimizing usability through a guided form, the software directly minimizes the user's cognitive effort, enabling non-experts to build baseline models without any prior knowledge of the notation. The guided interface represents only one of the potential input methods envisioned for the platform. Therefore, the software architecture is strictly modular and decoupled to make it easier for future integrations. To serve as an effective baseline for expert refinement, the generated model must be exportable to commercial platforms and synthetically correct to prevent downstream rework. Although the primary objective is to generate a baseline model, the system must remain strictly robust enough to manage diverse process logic and encompass the most frequently utilized BPMN notation elements without losing semantic integrity.
Moving from requirements to architectural execution, this diagram highlights our decoupled architecture. The process begins at the front-end input, where the guided form captures user responses and translates them into a structured JSON internal representation. This data feeds the back-end generation engine, which serves as a universal translator, rendering and returning a valid BPMN diagram to the real-time display. Moving on to the UI now. The interface first guides the user through the process core definitions such as name, participants, and start events. Then, the user is prompted to add as many elements as necessary for his process, with the system subsequently asking for the type, subtype, name or amount of divergencies, and the participant. As shown in the image, we have an activity of subtype default called separate the pieces and assign it to the lane of the production participant, which is the first lane in the image. As soon as new elements are added, the diagram updates in real time, ensuring continuous structural feedback for the user. Finally, we have the results or the evaluation part of the DSRM methodology. The research was evaluated in two ways. Firstly, by using an expert benchmark test. The intention was to evaluate the tool capability to replicate models. We replicated experts validated models in the tool and compared it to their original versions. As shown in the table, with a few of the test cases used, all models generated a valid BPMN model with only a few caveats. Mostly of them were sequency flow crossing over name label or over one another. As shown in the example, the generated model was very close to the validation model, except for the sequence flow crossing the name label on the intermediate event. Secondly, we evaluated the two perceived usability through an empirical case study with 83 volunteer undergraduate students. To capture their first-hand feedback, we utilized a comprehensive questionnaire combining the standardized system usability scale with targeted user experience metrics. The results were outstanding. The software achieved an average SUS score of 76.7, classifying its usability as excellent. Furthermore, on a 5-point scale, the simplicity of the diagram construction scored a height 4.31, while the student's perception of model equivalence to the original benchmark reached 4.07. In conclusion, G-BPMT proves that structured guided inputs can reliably generate valid BPMN models. By achieving high perceived usability, the tool successfully lowers technical entry barriers, fostering much clearer communication between analysts, and domain experts. Ultimately, delivering this automated baseline shifts the modeler's focus from tedious manual translation to high-level refinement, drastically streamlining the initial elicitation phase. Regarding our research limitations, restricting the tool to a subset of BPMN elements bridges the knowledge gap for novices, but limits the representation of advanced structures like complex subprocesses. Furthermore, our initial validation was conducted in a controlled academic settings, meaning further field testing is required to confirm real-world utility in complex enterprise environments. To address these boundaries, our future work will focus on integrating large language models to autonomously process unstructured text and voice inputs into our structured JSON schema, while expanding empirical testing directly to non-technical stakeholders in real-world contexts. Thanks for everyone's attention.